Hello everybody, welcome to today's presentation. My name is Brad Elkins and I'm with EOS Remediation. I'll be the moderator for today's webinar. The topic of today's discussion is going to be biogeochemical transformation of chlorinated solvents, and our speaker today is Dr. Pat Evans of CDM Smith. A quick introduction for Pat. Pat is the Vice President at CDM Smith in Bellevue, Washington. He has over 30 years of experience and has received a PhD in chemical engineering and conducted postdoctoral research in environmental microbiology. He conducts applied research and development in the areas of remediation, energy, drinking water, and wastewater. And we are very pleased to have him today to speak with us. Before we get started, though, I want to share with you a little bit about EOS Remediation and who we are and what we do. EOS Remediation is the original developer of the emulsified oil technology for in situ bioremediation. We've been in business since 2002. Some things that I want to make you guys aware of today: if you haven't already, please visit our website and check out our new EOS design tool. This is a new rehash of the old design tool. Some folks in the industry who have been around for a while may remember we had a design tool that we made available, and we have since revised that and made it available through our website. So if you haven't, please visit our website and check that out. Also, for our audience today that may be listening in from Australia, if they're up that late, we are going to be doing a combined workshop with Microbial Insights in both Sydney and Melbourne, Australia on October 20th and 27th. And finally, if you're in the southeast area and you're going to be making it down to the Florida Remediation Conference in October, we will have a booth there, and my fingers crossed, I've submitted an abstract, so hopefully I'll have a talk as well that if you happen to stop by that conference, you can come check that out as well. So without further ado, I'm going to go ahead and I'm going to turn it over to Pat and let him get started with today's presentation.
Okay, so welcome everyone, and I want to thank EOS for the opportunity to speak with you today. And so we're going to talk about chlorinated solvents and this technology called biogeochemical transformation. And first, talking about the problem, we're continue to be faced with DNAPLs, with large dilute plumes of chlorinated solvents. And it seems the more we investigate this, the more complex the problem gets and the more difficult it gets to solve. And one of the ways that we approach this problem is by looking at bioremediation, or looking at chemical oxidation, or using thermal treatment. But recently we've been looking at combined technologies and ways of integrating multiple processes in order to get better synergy and more cost-effective and faster treatment, and hopefully reducing things like back diffusion. And so that's what we're going to talk about today, is this process called biogeochemical transformation. We held a workshop back in 2007. This document was produced by CDM Smith in collaboration with the Air Force, the Navy, and ESTCP. You can see the link to it down at the bottom where you can access that. And in that, we defined biogeochemical transformation as processes where contaminants are degraded by abiotic reactions, and that can be either caused by naturally occurring or biogenically formed minerals. And so what is that all about? Well, if we take a look here, there are a number of different processes that or mechanisms that can lead to this. One is all iron sulfide mediated transformation. Here we have sulfate, which can be reduced by sulfate-reducing bacteria in the presence of an electron donor, and this can produce sulfide. We also have ferric iron, or ferric iron oxyhydroxides, that can be present as coatings on sand, or maybe we can add these minerals to the subsurface in minerals such as magnetite or hematite. And there are iron-reducing bacteria that, in the presence of an electron donor, that can also reduce this to ferrous iron, or the sulfide that's produced up here can abiotically reduce this ferric iron and produce ferrous iron. These two can combine and then form iron sulfide coatings on sand grains or mineral grains that are present in the subsurface. And what is really cool about this is that these iron sulfides, whether they be minerals such as maconite or pyrite or others, can abiotically degrade TCE to acetylene and chloride by a beta elimination pathway. And so what's happening here is rather than the typical biological reductive dechlorination where you're going from TCE to cis-dichloroethene to vinyl chloride to ethene, we aren't accumulating those daughter products in the process, and that's one of the advantages of this. Now, while we're going to talk mostly about iron sulfide mediated transformation today, this isn't the only mechanism for biogeochemical transformation. We know that green rust can play a role in this. Magnetite is something that's recently gained a lot of interest, and it can also have certain reactivity. And then also we can have ferrous iron chemisorption mediated transformation. Well, what's that? Well, that is where we have ferrous iron sorbing or chemisorbing to different minerals such as magnetite, and maybe this is acting as a semiconductor. We don't know a lot about this, but this can also result in the degradation of these compounds. Now the EPA, Tom Hay, John Wilson, formerly with the EPA, had put this document out several years ago. You can see the citation for it down below out of Ada, Oklahoma. And this is a great document. It has descriptions of different minerals, much more detail than what I've presented to you, and a great resource not only for giving you an overview of the different processes, but also gives you some techniques for analyzing for those minerals and how to go forward. So getting to the practical side of this technology is not brand new. It's been implemented for quite a few years. The Air Force has been a pioneer in this in terms of putting in situ biowalls and bioreactors at different Air Force sites around the country. It can also be implemented by injecting different amendments into the ground, and then it can also occur naturally. I think one of the most interesting aspects of this technology is looking at post-remediation M&A. What we're finding is that if we go ahead and implement bioremediation, we end up growing a lot of bacteria, and it was previously thought, still is thought, that the bugs that are produced end up being a source of reducing power through endogenous respiration, and that can contribute to ongoing reductive dechlorination and preventing or attenuating any back diffusion that may be occurring. But now we're thinking about it a little bit differently, is that it's not just the dead bugs that are promoting this process. It's also the bioremediation process is reducing the natural minerals present in the subsurface, where in effect we're charging a battery, and that battery then can go ahead and continue to promote the reductive dechlorination process for years. We don't know how long, and it's going to be site-specific, but we are beginning to realize that that's an important process. So a couple of slides here provided by Bruce Henry of Parsons and some projects that they did. One application is an in situ biowall. This is showing a DeWind one-pass trencher that's being put in a biowall, a trench, such as shown here. And in this biowall at Altus Air Force Base in Oklahoma used a number of different materials like cotton gin compost, sand that would have some iron oxide coatings on it, mulch, different types of mulch, and then as groundwater containing a number of different VOCs would decrease into the biowall, and this was a good cutoff mechanism for this very large dilute plume. Another way is an in situ bioreactor, where instead of putting in a trench, have an excavation, go ahead and put your mulch mixture into this. You can put whatever you want in there. And then you have a pump that's recirculating water through this. It can be solar powered. And then we get degradation through this biogeochemical transformation process in the bioreactor. And then as the water leaves the bottom of the bioreactor, it can end up contributing to biodegradation or biogeochemical transformation in the subsurface as well. So process has a lot of advantages. And one is it's not completely dependent or not at all dependent on D. halococoides, and it uses a number of different mechanisms for contaminant degradation. And this whole idea of providing additional reducing potential for monitored natural attenuation has a certain advantage, but has certain disadvantages as well. It's much newer than bioremediation. We don't know as much about it. It's in many ways a black box. We implement it in an ad hoc way. We don't have a lot of engineering guidance. So a lot of the research we've been doing is to try to turn that around. So one of the things that we did in work that was funded by ESTCP and the Navy, this was looking at a number of different biowalls around the country. These include biowalls at Altus Air Force Base, Dover Air Force Base, and the Seneca Army Depot in New York. And then also looking at the EPA had done a column study using materials from Altus Air Force Base. John Wilson had led this. And these biowalls and the columns had a number of different materials, different compositions of mulch, different types of mulch, different types of iron oxide. Some of them were amended with gypsum as a source of sulfate. And then we had different residence times. They were installed at different years. And then the groundwater had different concentrations of sulfate, very high concentrations in the thousands ppm down to very low concentrations. So one of the things we took a look at is, well, what was the pattern of transformation of the VOCs in these biowalls? So what we see here is the total micromoles per liter of VOCs, and or the individual VOC concentrations, and we see TCE is decreasing up gradient into the biowall, and then we see cis-DCE and vinyl chloride is increasing as it goes into the biowall. This is what we call a biotic transformation pattern, standard reductive dechlorination, where TCE is reduced to cis-dichloroethane and then to vinyl chloride. This is not biogeochemical transformation. This is not what we're looking for, but in this particular biowall, that's what was happening. Now, at Altus Air Force Base at the SS-17 biowall, we did see this biogeochemical transformation, and what we characterized this as an abiotic transformation pattern. Here, we saw a reduction of all VOCs and no accumulation of any one particular VOC. Down gradient appears to be some back diffusion. That's what we believe is going on, but at least in the biowall, we're getting completely reduction without accumulation of those daughter products. So this is one way to characterize this, and what we've proposed here is a term called the abiotic fraction, or F-abiotic. And this is something that's very easy for you to go ahead and calculate and to characterize biowalls, bioreactors, even plumes that contain different chlorinated solvents. And you can say, is it being removed by one of these two patterns? You go ahead and take the molar sum of all of the VOCs, including ethene up gradient, and then also in the biowall or down gradient, and you look at the percent reduction. And if you have a value of 1, it's an abiotic pattern. If it's 0, it's a biotic pattern. Now, this isn't going to consider all of the different possibilities that you may be able to get biological degradation of ethene, but it's a good start and a very easy and practical tool to characterize these. And if you have a term of 0, then you definitely know you have a biotic pattern. If you have 1, it may be biotic and abiotic, maybe even complete absorption, but at least you know you're completely removing all your VOCs. And this can be useful as shown right here. In looking at all of these different sites, we found that the F-abiotic was at Altus Air Force Base and at the EPA column B3, which is based on Altus Air Force Base. We had quite high values of F-abiotic, whereas at Dover Air Force Base it was quite low. And if we compare that to the first order rate constant, we see an association between these two. So some indication that this is a useful pattern and pretty easy to use. Now, why did one work and why did the other one not work? People have used acid volatile sulfide and chromium extractable sulfur analyses to try to understand what's going on here. This is part of the amoeba protocol that was developed by the Air Force, and this was formerly offered as a service by microseeps. They've since decided not to do that anymore, but what I understand is that Prima Environmental is now going to be offering this as a service. And it has some value, but in the research that we did, we found it didn't have a correlation with biogeochemical transformation. We found out that in certain cases, such as the EPA column, we did have high values of the AVS and CRES, but we also had, and this had high removal rates and a high abiotic fraction, but we also saw high values, similar values of these two parameters at Dover Air Force Base, where we had low rate constants and low F-abiotic fraction. We also had low values of AVS and CRES, where we had high rates of VOC removal, and similar to this. So this has some questions, and so, well, what are we left with? Well, one thing we can take a look at is, well, what kind of minerals are there? You can use a technique such as electron microprobe, a bit more expensive, more specialized, but certain universities are capable of doing this. And it's essentially a scanning electron microscope, which you can also look at elemental composition. So here's some photomicrographs from the EPA column B3 samples that we evaluated as part of this. And what we see here is we see these circular patterns, which are called framboids. They are predominantly iron sulfide, mainly pyrite. We also have individual iron sulfide grains. And then we have other things such as quartz and different parent iron oxides, such as hematite or magnetite. If we take a look at one of the biowalls in a close-up, we see what this framboid is. Again, it's small, little, about 1 micron particles that agglomerate together in a roughly spherical form called a framboid. And some have previously believed that pyrite is not reactive. It turns out is quite reactive and can have surface area based rate constants that are actually greater than iron monosulfides. So pyrite is something that you definitely don't want to ignore. So by using an electron microprobe, you can determine, well, are these present or not? Now, if you don't find them, that doesn't necessarily mean they're not there, because there could be nanoparticles that you can't see with this technology. But if you do see them, that's pretty good evidence that they are there. Now, it's not just these framboids that are formed. We also see that there are coatings on iron minerals. This is a mineral of magnetite from the EPA column study, and then we find this has been coated with sulfur into these nooks and crannies in the magnetite particle. And so these are iron sulfides as well, and they have potential reactivity as well. Now, we can also take a look at the grain size of these different minerals. If we take a look at Dover Air Force Base compared to Altus Air Force Base, we find that the iron sulfides, median grain size about 1 micron, whereas Dover Air Force Base, it's more on the order of about 8 microns, also has some oxide coatings. And this is really important with respect to the reactivity. These reactions are surface-mediated reactions. The VOCs need to contact the surface in order to be decomposed by this beta elimination pathway. So the greater the surface area, the greater the reaction rate. As an example, if we take a look here at Dover Air Force Base, about 8 microns, we have a calculated surface area of about 0.15 meters squared per gram, compared to Altus, OU1, about 1 microns, about 1.2, so about 10-fold difference in the surface area, and all other things being equal, we can expect about 10 times the reactivity. Well, what if we had nanoparticles, which we can't see? Look at what the surface area of these are. So this can be very important, but it's very difficult to find these in a complex soil or mulch environment. If we also do some geochemical modeling and use the electron microprobe, we can find that we can see distributions of these grain sizes. With Altus Air Force Base, we saw this median grain size of about 1 micron or 1,000 nanometers, and it was mainly a monodisperse distribution. Where if we look at Dover Air Force Base, we see a polydisperse distribution of different grain sizes. And this is indicative of a process called Ostwald ripening, where we're essentially forming crystals in much like an onion layer. And this is indicative that we have a poor geochemical environment for production of these minerals. What we want are high surface area minerals. We want nucleation to occur rather than crystal growth. And Dover Air Force Base has a relatively flat groundwater gradient, sometimes reversing. We can also see rainwater that can infiltrate into the subsurface, bringing dissolved oxygen. And these things are all indicative of what we don't want. And if we do geochemical modeling using a program called FREAK, we can find out what the saturation index of our different potentially reactive minerals like maconite or pyrite. Magnetite is a parent iron oxides, and we find it has a negative saturation index at these different places, which indicates it has a propensity to dissolve, which is good. And then we have certain things like pyrite, which are supersaturated, which is good. And then depending on which site, we have different degrees of supersaturation, undersaturation, or near saturation. So looking into this can give us some insight, but it doesn't give us a practical thing or quantitative numbers saying, are we going to be having, what rates are we going to have of degradation? That's ultimately what we're looking for, is the rates of VOC destruction. Well, we can look at another parameter here, which we've proposed, which is the volumetric sulfate consumption rate, which can be very important for these iron sulfide systems. What is this RSO for? It's taking a look at the grams or milligrams of sulfate that are removed per unit volume of reaction area per unit time. So this could be the reaction area in a biowall or a bioreactor, or it could be along the distance of a plume in an injection system or in a natural attenuation system. We calculate this by calculating the change of sulfate concentration, up gradient and down gradient, and then dividing this, multiplying it by the flow rate, dividing it by the pore volume, or in other words, dividing it by the hydraulic residence time, say if you have a biowall or a bioreactor, or by the groundwater travel time. So very easy to calculate. And what does this look like? Well, if we take a look at these data I presented before and we compare this to the volumetric sulfate consumption rate, we find in cases where we have high first-order rate constants and high abiotic fractions, we have high volumetric sulfate consumption rates. And so this is an indication of biological activity, because sulfate likely isn't going to be removed by any other process other than a biological one. And that sulfate is going to sulfide, and that sulfide is important with respect to formation of these iron sulfide minerals. So this is another very practical and easy to calculate parameter that can be very helpful. So we see there are a number of different factors that affect reactive iron sulfide production. And we can look at all of these, and in the next part of this presentation we're going to look into it a little bit more deeply, but ultimately what it comes down to is two different reactions, two competing reactions. First is the formation of these iron sulfides. We talked about the sulfate, volumetric sulfate consumption rate. That's all about producing the sulfide. But we also have to have that iron present. And that's going to be driven by a certain rate constant, which is dependent on things such as the biological activity, electron donor, geochemistry, and this is going to lead to formation of these reactive iron sulfide minerals. So that's good. But at the same time, we have continuous deactivation of these minerals. This can occur through oxidation of the mineral surfaces, either by when it reacts with TCE, for example, or maybe reacts with dissolved oxygen. It can also occur by crystal growth and loss of surface area. Bottom line is we want K1 greater than K2, and we need to optimize these different factors in order to achieve this. But first we have to find out which factors are the most important. We did a large column study funded by the Air Force looking at these different factors to try to see what would cause or what would promote or optimize this biogeochemical transformation. We looked at different forms of iron oxides, different pH, sulfate concentrations, gypsum, groundwater velocities, which translated into residence times. And these were all mulch columns, but in some of them we amended them with vegetable oil as an additional electron donor. Here's a picture of us doing this in our Environmental Technologies Laboratory in Bellevue, Washington. So about 48 columns there, quite complex system. And here are some examples of the patterns that we saw from a couple of different columns. This is a biotic pattern from column number 6, where we're seeing TCE coming in and initially being absorbed, but then breaking through and then eventually being removed by a biotic transformation pattern, where this TCE is just being converted into cis-DCE, these green triangles. So under these conditions, that's what we saw, and this is not what we were hoping for, but what we wanted to do is find out, well, what conditions would lead to a biotic transformation compared to a biogeochemical transformation pattern, as in column number 31. Here we see the TC is removed, and slowly we see TC is breaking through. But for a period of almost a year, we're getting significant removal of TCE without accumulation of cis-dichloroethane. We didn't detect any vinyl chloride or any ethene in the effluents here or in the gas. And so we're seeing this biogeochemical transformation pattern. Well, we had more than 2 columns, and I'm not going to show you 48 columns worth of data. We had to use some statistical analysis to figure out what's going on here. We used a technique called principal coordinates analysis. This is essentially a multivariate statistical technique that allows you to take a complex data set. In this case, it was time series data for TCE and cis-dichloroethane and total VOC removal, and look at the total variance in that data set and try to capture it in these terms called principal coordinates or axes. And if we can most of the variance and describe that by 2 or 3 of these PCOs, then we're successful, and that's what we did here. So what we then do is we take these principal coordinates and have them on the X and Y axis, and we plot each of these columns. So here's column 31, that did really well, and then we have our other columns all designated by these numbers. And so they're separated now out in space, this 2-dimensional space. If you can imagine, there'd be a 3rd dimension, which would be PCO3. And then as an overlay plot, we can plot the other parameters, such as percent TCE removal. And that's shown in this color scale here with these contours, 80% removal, 60% removal. And so blue being the higher percent removal of TCE. And what we see here is up in the upper right-hand corner, actually about half of this, we see where we've got the zone of high TCE removal, greater than about 50–60%. And so this was associated with this high PCO1 and higher PCO2, but there were some areas where it was intermediate as well. So we're able to separate columns that did well in TCE removal from columns that did not do well in TCE removal. If we look at DCE production, so this is our biotic transformation of TCE into cis-DCE, we find out that this is down in this lower right-hand corner. So again, this is where this biotic transformation pattern is. If we take a look at the biogeochemical transformation, so this is complete removal of TCE and cis-DCE, and so no accumulation of our daughter products, we find that this is up in this zone. And so now let's compare it to the previous 2. Here's where our biotic transformation pattern was, so very clearly separated from our biogeochemical VOC transformation pattern, and both of these overlapping in TCE. So we're getting TCE removal here by a biological transformation pattern, and here an abiotic transformation pattern. So we wanted to find out, well, what are the factors that cause this separation? We want to be here, not down here. We did analysis of variance and identifying p-values to find out what are the significant factors. The ones in bold are the ones that were significant. Groundwater sulfate, vegetable oil, and flow rate or residence time were the most significant. Interestingly, if you look at 0.05 as an indicator, these different iron species weren't significant as determined by this ANOVA, but however, we do know they're important. I'll show you why in a second here. So let's look at some of these factors. Let's look at that sulfate, since that was one of the significant factors. Here we're showing the same PCO plot, and we're looking at the effluent sulfate concentration in these contours, and we find it was lowest in the area where we had high TCE removal. So the low sulfate could be because of 2 reasons. One, we had influent sulfate, groundwater, that was very low, which was for some of the columns. Or we could have high influence sulfate in the influent and high sulfate removal. And that's in this zone right here that overlapped with the TCE removal. If we look at effluent methane concentration, the blue being the high concentration, it's exactly in the same area. Well, this makes sense. You're going to have high sulfate, you're going to inhibit methanogenesis. And so we saw that. But what about this sulfate consumption? This is that volumetric sulfate consumption rate I was telling you about. So here we're seeing consumption up about 1,000 ppm or more in blue and down around 0 more in the orange. This, in general, overlaps with our biogeochemical transformation pattern. There are some exceptions. This is a complex data set, and so, but if we look at the preponderance of the columns, they are shown up in this area, which corresponds to biogeochemical VOC removal, which also corresponds to high sulfate consumption, validating that that's an important process. What else? A lot of these columns also had either hematite and or magnetite. And so what we find from this is we've got several parameters that are really important, including the sulfate consumption, the presence of iron oxides such as hematite or magnetite, and then also what's not shown here is sufficient residence time and electron donor to promote the reduction of the sulfate. So with all of these different parameters, we'd like to be able to monitor what's going on. We have a lot of different tools that we can look at. And so we took, in another project, we took a look at some of these tools and how we could use those to gauge the optimization of a system and a performance of a system. Here's shown some passive flux meters that were created by Mike Annable at the University of Florida. And these are used for looking at this volumetric sulfate flux. I had mentioned that you can go ahead and take grab samples of the sulfate and look at groundwater flow rates or residence times, but using these PFMs where you put ion exchange resins is a better way to do it because you can use these both to determine groundwater velocity and use this to use sulfate flux, and from that get your volumetric sulfate consumption rate. You would need to put these one in an up gradient location and one in a down gradient location to get that number. So this was an experiment that was done by Brown and Caldwell under funding by the Air Force in collaboration with the EPA. And CDM Smith tagged on to this, also with funding from the Air Force, to implement these monitoring tools and try to figure out what was going on. So what Brown and Caldwell did is they looked at this OU1 biowall section at Altos Air Force Base, which wasn't performing very well. It had a biotic transformation pattern. We were just converting TC into cis-DCE and wanted to optimize the system to get it working again. And so in these two areas here, what they did is they ended up amending this section with electron donor only. They used emulsified vegetable oil and also lactic acid or lactate. And then down in this section here, they hypothesized that, well, it may be limiting in iron. And so let's go ahead and add some emulsified vegetable oil, but let's also add some ferrous lactate and some hematite. And then for our study, we need to have an unamended section, so we also looked at this. And so in these three areas, we put in situ microcosms, passive flux meters, and took grab samples. And then we also did this in up gradient wells as well as groundwater was flowing this way. So let's take a look at what we saw. Well, here's the unamended control area. And each of these plots are the same. We have the up gradient concentrations over time here, VOC molar, and each of these being the different species, TCE, cis-dichloroethane, and vinyl chloride, the little touch of ethene right here, and here's what we see in the biowall. We see things changing over time, but in general, we're seeing very similar patterns. Nothing is happening over time in terms of total removal, and we're seeing just a transformation of TCE into cis-dichloroethane and vinyl chloride. So that's what we were trying to get away from. If we take a look at the biowall that was amended with organics, what we find up gradient is that it's mostly TCE with DCE, changed over time, but generally ranging on the order of 10 or so micromoles per liter total VOCs. In the biowall, we started sampling after the amendment had already been done, and so we already started to see the process going on. We saw that we were having a lot of vinyl chloride here and some cis-dichloroethane, but eventually it was reduced down to well below 1 micromole per liter, so significant biogeochemical transformation pattern where we're removing these VOCs and not seeing any daughter products. So this was without the iron amendment, just the organics being added. If we add the amendment, we see a similar pattern, maybe not quite as good, but still we're seeing, look at the scale, 20 micromolar versus 1.4 micromolar. We're still getting over 90% removal of these VOCs, and it's increasing over time. Now we had another biowall up here at the same site, which is the SS17 biowall. This is like the Energizer Bunny. This is the biowall that keeps on ticking. It's removing these VOCs. we're getting less than 1 pp micromole per liter of the different VOCs. And so we have 4 different biowall sections here. Why are they different? Why are some working and why are some not working? Well, let's take a look at a couple of things here. One big difference was sulfide concentrations. In the unamended OU1 biowall, we had very high sulfide concentrations. And in fact, in the OU1 EVO biowall and the EVO iron amended biowall, before the amendment, the sulfide concentrations were also high. But as soon as the amendment was done, the sulfide concentrations started to decrease and got down near where this SS17 biowall was working, which was very good. If we look at total VOC removal, initially this EVO biowall, OU1, wasn't doing very well. This is this abiotic fraction of 0, but then it got up near 1. We're getting complete removal, whereas the unamended one not doing well at all. And so this was one indication that sulfide was somehow associated with poor performance. Now, this is where it really gets interesting. If we take a look at these passive flux meters for the volumetric sulfate consumption rate, we see high volumetric sulfate consumption rate in the SS17 biowall, the amended OU1 biowalls, but we have low volumetric sulfate consumption in the unamended biowall. So this is rather curious. We had high sulfide in this biowall, but low sulfate consumption, which seems a little counterintuitive, but I'll explain what's going on here in a couple of slides. What is also worth pointing out is that this association somewhat correlates with the first order rates for VOC removal in 1 per day. We're getting low rates of total VOC removal in the unamended biowall compared to these other biowalls. So this volumetric sulfate consumption rate and the sulfide concentrations are key to the performance. And we also saw ORP was related to this too. When you had a high sulfide, you had much lower ORP, indicating that having a really low ORP isn't always a good thing. Well, so we know that that sulfide was important, and we know the sulfate was important. But what caused that OU1 EVO amended biowall to change over time? Well, we added all these electron donors in the form of lactic acid and emulsified vegetable oil, and of course we saw very high dissolved organic carbon, over 1,000 ppm. Now that decreased over time, but initially it was very high. That also resulted in the formation of very high concentrations of volatile fatty acids, over 10 milliequivalents per liter. What did both of these things cause? pH to drop. And so that pH dropping is very important because it affects the surfaces of these iron oxides, these iron sulfides. I'd mentioned that we have to have a constant generation of these reactive iron sulfides, and that can be by having iron oxides that can be reduced or can absorb sulfide, and we also have to have that sulfate reduction. Well, this pH is very key to what happened here. What we saw at the SS17 biowall is that there we had magnetite, higher concentrations of iron oxides, and then also that biowall is younger. So what we think is that those iron oxides hadn't been passivated, and so they were still active and capable of absorbing sulfide and forming these iron sulfide minerals, which would be reactive and abiotically destroy TCE. There was plenty of organic carbon as well in order to drive this reaction of sulfate going to sulfide. So that's what was going on at the SS17 biowall. If we take a look at the OU1 biowall, what had happened is, via the indirect evidence, we believe these iron oxides were passivated. And this prevented absorption of sulfide onto these iron oxides, and that's why we had high sulfide concentrations. And so we didn't see this reaction going on. We know this because we have the high sulfide, and we know that we had total iron concentrations that were quite high, greater than 1% in the biowall. So we weren't limited in iron, but it wasn't capable of absorbing the sulfide. When we added our electron donors, what we did is we dropped that pH and we generated VFAs. This drove more of the sulfate reduction, which is produced sulfide, which is why we saw a higher volumetric sulfate consumption rate after we added those amendments. But also our sulfide concentration went down. Why? Because that low pH appears to have activated these formerly passivated iron oxides and allowed sulfide to absorb onto the newly fresh iron oxide surfaces, form new generated iron sulfides, which could cause this reaction. So what we did is we ended up increasing that K1, the formation of these iron sulfides, and we decreased the rate of that deactivation, K2, of iron sulfides, and we ended up optimizing the biowall, rejuvenating it, and we used these different monitoring tools to cause that to happen. So we had a lot of different things going on here, and it was really a combination of biological mechanisms, chemical mechanisms, physical mechanisms, and all of these needed to be considered together to be able to put a conceptual site model, if you will, on what was going on here. So we have a lot of different tools. These are ones that we found useful for this particular project. There are others. We looked at quantitative polymerase chain reaction. We didn't get any useful data out of that, but that was just at this site. That doesn't mean that that may not be useful at other sites. But this is a list of things that are very easy to use, with the possible exception of the electron microprobe, which is a little more expensive. But all these others are conventional analyses, and maybe some new ones using positive flux meters, and just different ways of looking at the data and looking at what's going on. I want to point out that it's not all about iron sulfides, though. Magnetite's very important as well. So magnetic susceptibility is another tool that's up and coming, and this is something that should be looked at as well. And we didn't focus on that in this particular project. We're currently doing a demonstration under the STCP to validate a lot of this data that we've generated here. And this is being done in Rhode Island at a Nike missile site. And we have three large column studies. These are about 8 feet in diameter, submerged in the ground. And this one has soil, native soil. These two have a mulch-sand mixture. And then these two are biogeochemical transformation reactors. So these are both amended with magnetite, and then we'll also have high sulfate coming into these. This one here has no magnetite and no sulfate, and then all three of these are amended with emulsified vegetable oil. And so what we're going to do is we anticipate that we're going to get this abiotic pattern and high removals, and here we're going to get more of a biotic pattern. So this project is just starting. I hope to be reporting on this in the next year or so. So I want to acknowledge the funding from Department of Defense, ESTCP, the Air Force Civil Engineering Center, and NAVFAC, and also a lot of individuals here, which I won't read all of these names, but they've all been instrumental in different ways in promoting this research and executing this research. And with that, I'd be happy to answer any questions. Thank you for your time.
All right, Pat, thank you so much for that excellent presentation. One question that came up, Pat, is could you comment on the role of buffers in this technology, such as like calcium carbonate?
Yes. So in the column study we didn't see an effect of pH. We had looked at 2 different influent pHs, 6.5 and 8. And the reason for that was in part buffering by the soil itself. Soil, as we know, has a high buffering capacity, and the effluent pH in the columns, all the columns were pretty much the same. But as you drop that pH, then by adding emulsified vegetable oil and going ahead and producing these acids, if you have a high buffering capacity in the groundwater, or you add, say, a buffer, then you're going to end up not decreasing the pH, and that may affect your ability to rejuvenate these iron oxides. Also, with high concentrations of calcium and carbonate, you can get calcium carbonate or calcite coatings on these iron oxides, and that can also result in a passivation of the iron oxides. So that's something to consider as well, and doing a calculation like using a Langular saturation index can give you some clues along those lines.
Okay. Another question is, Pat, you talked specifically about chlorinated ethenes. Would any of these processes you discussed, would they work equally as well on the ethane, such as like carbon tetrachloride?
Good question. There has been some work looking at sulfides and some of these different minerals, working with carbon tet, and yes, it does work with that. With some of the chlorinated ethanes, so far, not a lot of data supporting that that would work, and there have been a lot of questions in terms of, well, how would this work with emerging contaminants like dioxane or perfluorinated compounds? To my knowledge, not a lot of research that has been done on that. A lot of stuff going on now with pharmaceuticals and personal care products, and these may have certain reactivity with this, but most of the research to date has been done with these chlorinated ethanes and with carbon tet, where those definitely do react.
All right. How do you calculate the sulfate consumption rate using the passive flux meter?
Okay, yeah, so what you do is you go ahead, you put in these passive flux meters, which Mike Annable and his company will be happy to sell you, and they would have both the change resins in there for absorbing or ion exchanging the sulfate, and then also activated carbon with the different alcohols to get the groundwater velocity. You'd put one in up gradient and one down gradient, or if you have a biowall, one up gradient and one in the biowall. Put it in for a period of time, and for our case it was a couple of weeks, but it may be more or less depending on your site. He's going to go ahead and take these and analyze them for sulfate and for the alcohols, and he's going to come back with a flux, which is grams of sulfate per square meter per day. And then from that, you're going to use that and the hydrogeological parameters, the groundwater flow rate and the such, and residence time, in order to convert that to a sulfate loading rate in the up gradient zone, grams per liter per day, and in the biowall and the down gradient zone, grams per liter per day. Then you're just going to subtract the two, and that gives you your consumption rate.
You talked in the presentation about some low pH situations. What about in situations where you have a high pH environment, maybe something that's in the caustic range, up above 9 standard units? Do you think that these processes would work well in that kind of a situation?
Yeah, so the iron sulfides, there's been a lot of basic research done by people like Liz Butler and Kim Hayes and the others looking at the reactivity of some of these minerals with respect to pH. And so you'll see variation in reactivity with pH. And so pH is very important. But in order to form the minerals, unless you do it chemically, you need to have the biology there to be able to reduce the sulfate. So if you get into a zone where you're, say, pH 10, you're not going to be very conducive to biological sulfate reduction, and you're not going to be able to form the sulfide, and therefore you're not going to be able to produce the iron sulfides. There's been some work where people have tried to just chemically generate these iron sulfides in situ, and to my knowledge, this hasn't been too successful. We don't know exactly why. My thought is that it's this biological process that is resulting in the constant formation of these, or the constant nucleation of these high surface area minerals, and that's key to making this process successful. The abiotic, you go ahead and you put, if you chemically generate them, you produce them, but then there's no longer any chemical incentive, if you will, to nucleate new minerals, and they will just start to grow and crystallize and lose their reactivity.
You spoke a lot about the iron sulfide, different mineral species. Have you guys looked at, or have you ever evaluated any other sulfite or sulfate minerals, such as like a barium sulfate?
Barium sulfate would not be reactive with these. This is a reductive process, and so you need a strongly reducing mineral in order to be able to reduce that trichloroethane. So sulfate is oxidized, and so it would not be effective whatsoever. So these are all sulfides, and you'll see stoichiometry between the iron and the sulfur will range from Fe, where 1 and S1 to Fe1 and S2. there's a whole range of stoichiometries in between there. But if you're looking at something like sulfate, that's not going to be reactive. Sulfite, bisulfite, that hasn't been looked at for chlorinated ethanes to my knowledge. I don't think it would be reactive. It can be quite reactive with, say, hexavalent chromium has been successful, but not with the chlorinated ethanes.
Would you describe more explicitly the passive and active activations of the iron minerals with respect to low and high pH?
Okay, so the I assume the questioner is asking about this rejuvenation at Altos Air Force Base.
I think that's right.
Is that correct? Is that correct?
I believe
okay.
so.
Okay, so at the ambient pH that the Altus OU1 biowall was at, there was conditions such as that, and we don't know them exactly, we didn't go into the mechanism of this in detail, but somehow these iron oxide coatings or iron sulfide coatings became oxidized, or the iron oxide coatings became coated maybe with a calcite layer or something like that. And at that pH, let's call it 8, we weren't able to absorb any more sulfide, and that's why we saw that high sulfide concentration. So we went ahead and we added, or Brown and Caldwell added the electron donors to this, and that ended up dropping the pH down to 6.5 or so. That ended up producing this acidic environment, which was able to then dissolve whatever these coatings were that were present on the iron oxides, or maybe it, just have a new clean surface, whether it's calcite or something else, we don't know. And that fresh surface now was capable of absorbing sulfide very well. If that didn't answer your question, please ask again.
When using the abiotic term, how do you quantify biogeochemical degradation when there's also some biological degradation occurring?
Yes, you can still use it in the same way, and what you and often what you're going to see is it's not solely biogeochemical and it's not solely biotic. In fact, in many of the columns that we saw, it was a mixed pattern. And the paper that we've written on this will be, it's in press with groundwater monitoring and research, and will be out hopefully in a month or so. And so in that, these mixed patterns, the abiotic would be between 0 and 1. And so you can still use this, and it's, again, not going to cleanly say, hey, it's 100% abiotic or it's 100% biotic. You're going to get this continuum between them. And so it's a tool, and it shouldn't be used to define mechanisms on a very, very fine level.
Last question, because we're starting to run out of time, is if you're interested in doing this, folks out there are interested in doing this, and they lack naturally occurring iron sulfide minerals, could they inject something like a nanoscale iron sulfide mineral into the aquifer?
Yes, so you could, and there are some companies that have worked on developing some of these things. One of the questions with injecting these nanoscale iron sulfides would be whether they are going to remain active or they're going to be passivated. My thought is they would probably become passivated. I think a better way would be injecting the iron oxides themselves and then injecting a source of sulfate and your electron donor. And so there are some new products out on the market that can go ahead and do that, and I think that's a wave of the future.
Okay, excellent. Again, Pat, I really appreciate your time today in presenting on this topic. It was a fantastic presentation. For those of you who would like a copy or like to view this presentation again, it will be made available through our website. Please visit eosremediation.com. There's going to be, if you haven't already, You'll need to register for use and gain access to our library, and by doing that, just click the login screen and it will take you through the process of how to register. There were several questions that we couldn't get to. We just don't have enough time to get to all of them, so if your question wasn't answered by Pat today, there's his contact information on the screen as well as my contact information, so please feel free to reach out to either one of us. Again, Pat, thank you so much for your time, and thank you everyone for listening. Have a great afternoon.
Thank you very much.